Hello. Okay. Good afternoon, everybody. So welcome to the second live session of the Parallel Computer Architecture course. And I think you've already finished 5 to 6 weeks in the subject and are doing the assignments, etc. very well. Okay, so if you have any questions, you can ask during the live session. You can, if you have joined the Teams meeting, you can put your questions in the Teams chat window. And if you're joining live on YouTube, you can also put your questions in the chat box. We also have shared the Google form with you where you can put your questions. So we already have a 3 to 4 questions in the Google form, so which we will address shortly.
Ma'am, there is a doubt I have. I just want to have. I would just want to understand like the difference between Dragon protocol and MESI protocol, like in cache coherence.
Okay. All right. Dragon protocol versus MESI.
Yes, MESI.
MESI protocol. Okay. So, all right. So we can quickly look at the two FSMs and then we'll start the differences. All right. So let me open the FSM slide. Give me a moment. I'm just opening the PPT. Okay, so we'll just quickly recap the MESI and then the Dragon and then do the comparison. So this MESI protocol or the MESI protocol was discussed during lecture 8. And it's a 4-stage protocol where the individual term has its meaning. The M is for modified, E is for exclusive, S is for shared, and I is for invalid. This is an invalidation-based protocol and used in write-back caches. Okay, so MESI is invalidation-based write-back. So you can keep noting the differences so that it's more clear to you at the end of our discussion. And MESI protocol builds on top of the MSI protocol, which did not have the exclusive state. So the E state was not there, and this protocol adds the extra E state. The benefit of having the E state is that when you want to read the data for the first time, if you are the only sharer in the system, you will have the exclusive access to it. So you need not inform other sharers about you wanting to read or write to that cache. Okay, right. So let me go to the FSM and maybe. So this is the FSM of the MESI protocol. If you don't have the block, that is the block is invalid, and the processor wants to read the block, we will send the processor read on the bus. So when this processor read signal goes, there are two chances that there are other sharers in the system. in which case you have to load the block in the S state. In case there are no other sharers of this block in the system, we can load this block in the exclusive state. So from state I, okay. So from the state I, you can either go to state S if there are other sharers. And how do we know this? Using the wired odd signal S. So we discussed this in the earlier slide that this is a snooping based protocol. All the cache controllers are snooping on this bus. And when a processor, say P0, wants to read a block, it will send the processor read request on this bus, which is the gray color line. And the other cache controllers have to keep snooping on this gray line. In case they have the address cached, they will say that, yes, I have the block and I am sharing it. Otherwise, they will not raise this line. So this shared signal will be turned to 1 if a processor has the block. Otherwise, it will be 0. Hence, if I do a OR, logical OR of all these wires, if the signal is 1, it means there are at least 1 or more sharers in the system. If the signal wired or signal is 0, means there are no sharers in the system. All right, so this is the signal S. I'm going to use the signal S in this FSM. So if the signal is true, means there are other sharers, and hence my next state is S. If the signal is false, that is S bar is true, then there are no sharers in the system and we go to the exclusive state. So this is state E. Okay. Now the advantage of state E is that this is the only cache in the full system which is accessing the block. Hence, if this processor decides to write to this block, it need not take permission from others. Okay, so on a processor write, we directly go from state E to state M. We don't have to send any signal on the bus. Alternately, of course, if I am in state S, and the processor wants to do a write. In this case, there are other sharers in the system, and these sharers will have to invalidate their blocks because MESI is a invalidation-based protocol. Okay, so on this arrow, on the processor write, we send a bus readx. Bus readx is a special signal which will indicate to all the sharers that they need to remove the copies from their local caches. Now, to see impact of this, the bus reader signal, suppose this P0 is sending the bus readx on the bus, and there is a processor P1 who has the block, and that processor should delete this block. So how will it delete it? It is part of the same FSM in the red color. So come to the state S, and now this state S is with the processor P1, which receives the bus readx from processor P0. So that is this red line. Okay, so when this other processor receives the bus readx, it understands that there is another processor wanting to modify this block, and hence this processor should delete it. So it will delete the block and move to state I. So from state S, we go to state I. In case the other processor has the block in state M modified, and it receives a bus readx, that is the bottom red arrow here. So this bus readx, it will again move from state M to I, and then there is an additional signal flush written here. Flush means that the processor is going to provide the latest copy of the data onto the bus. So it doesn't care where the data goes. It just pushed the copy on the bus, and the processor P0, which is the new reader into the system, is going to pick up this block. Okay, so that is the transition across these two states. So from invalid, I can go to shared or to exclusive on a processor read. On a processor write, from exclusive directly to M. However, if you have a processor write from I or S, in I, we don't know whether there are sharers. In S, we know that there are multiple sharers. So in both these cases, we need to inform the other sharers about our intent to write. Hence, from I and S on a processor write, you have to send the bus readx. And now you already saw that on a bus readx, we move from S to I, M to I, and as well as E to I. In all three cases, the other caches will go to the invalid state, and the new writer will go to the state M. For writing, we always go to the state M.
Ma'am, basically only one processor can stay in M state at any point of time.
Correct.
Like, okay.
Correct.
So
only one state can stay in M. Even in Dragon, exactly one processor can stay in state SM. So the M in Messi maps to the SM, not exactly mapping, but analogous. It is analogous to the state SM of Dragon. And the state S here, the state S of Messi has single meaning that multiple sharers all have read-only copies. They don't have modified copies. So all the sharers having the copy in the state S have clean copy. Clean meaning the memory and the copy in this is exactly the same. If there is a cache with state M, this is the only cache having the copy. There are no S states. There are no E states. There is exactly one processor with the state M. It has the modified copy and the memory's copy is not up to date. So that is the meaning in meaning of M and S in the Messi protocol. Let us go to the Dragon and then we will again highlight the two differences. Okay. Okay, so it's the Dragon protocol. Okay, right. So in the Dragon protocol, it is what is the type? It is different than the Messi. It is update-based protocol and write back, of course, write back caches. So Messi is also write back, Dragon is also write back, but Messi is invalidation-based protocol and Dragon is update-based protocol. Okay, because it is update-based, it has a different semantics than the Messi protocol. Okay, so here for clarity or not to clutter the diagram, I did not give the I state, but you can assume that invalid state is there and then all the arrows come from the invalid state. Right. So here, the first time when there is a processor read miss or a processor read signal, this one, we again check the shared wire dot signal S. If there are no sharers, we go to state E. And if there are sharers, the left-hand side, you will go to state S. Okay, so it's state S. Now the state S in Messi is same as the state SC in Dragon protocol. Okay, because it essentially says it's a shared block, but clean. The C subscript is for clean. And in Messi, you already know that the state S is always clean. Clean meaning the memory and the cache have the identical copies. So when I'm in state SC, there could be multiple of these. The copy in the cache is exactly the same across the system. So this is a clean shared copy. This is for read. Now, when I have to, coming back to E. So in state E, if there is a read, continue reading. If there is a write, then we will go to state M. Okay, we don't go to SM, whereas M and SM are again similar meaning. M is a modified block, SM is also a modified block, but M says that I am the only cache having this data in modified state, same as the Messi protocol. But we already have an additional state SM, which says that I have the most up-to-date copy, but there are other caches in the system sharing the block. Now, why are they sharing the block? Why didn't they remove it? Because this is a update-based protocol. Messi was an invalidation-based protocol. So whenever there is a write request, everybody has to delete their blocks. Whereas Dragon is an update-based protocol. Hence, whenever there is a write request, we don't delete others' blocks, but the new writer in the system broadcasts the update across the system so that others can pick it up. Okay, hence we have two modified states. So from E, we will go to state M because this is a single cache in the system. The single cache, we go to the state M and then perform the reads and the writes. Now, whether when new readers and writers come into the system, we will not be in EM. We will go to the S state. Now, there are two S states. One is a shared clean and one is a shared modified. Okay. Now, let's see this. In state E, when a new reader comes, a bus read signal comes, means one more cache wants to read. You know that this cache has it as a clean copy. The new one wants to do a read. So both copies are going to be clean. Hence, we go to SC. All right. So we go to SC because there's a bus read signal. Okay. Then, when there are multiple sharers, clean copies, and a write request comes. So there is a cache which wants to write. Now, when somebody will write, that cache will have the modified copy. In messy, what will we do? We will go to the state M and delete all the other copies. Here, we are not deleting the other copies, but we will go to the state SM. So the new writer on a processor write goes to the state SM. But while doing it, what it does, it will send a bus update transaction on the bus. By sending this bus update, it is actually broadcasting the data which it is modified. So it modifies, it sends the data that I modified the variable X from 5 to 10, and it sends it on the bus. Now, whoever was sharing this data will pick it up and update their local copies. What will be the state of these others who have picked it up? It will be SC only because they did not change it. They have taken the data from the bus, so they will not change the state. But the processor which changes the data will move from SC to SM. So this processor will move from SC to SM because it has modified the data. It is kind of an owner of this block. So it will move to the state SM. All right, so it will stay in this SM, and whenever there are future reads or writes, it will stay in the same state because there is no new writer yet into the system. Okay, so for on every write, while I am in SM, I'm going to send the bus update. So I keep on changing this variable X to 5, 10, 15, 20. Every write is going to be a broadcast on the system using the bus update signal. So I'm going to keep sending the block and still stay in the same SM state. Now, while we are in SM, and there are two chances that there is a new reader into the system. Already there are 4 or 5 readers. A 6th reader wants to read the block. Now, 5 are already sharing the block. 6th cache wants to read the block. So where will the new fresh data come from? In messy, this fresh data comes from the main memory because when a new reader comes, no cache takes responsibility of sharing except for some optimizations. But in general, we can assume that the memory has the up-to-date copy, it will give the data. But if there is a state M in the messy protocol, the cache having the M state will provide the data to the new reader. And then both of them will become state S. But in Dragon, when a new reader comes, who will provide the data? The cache in the state SM or M, of course, if there's a single M existing. So a new reader, look at this red arrow at the bottom. When a bus read signal comes, this cache is in SM. So it puts a flush. So now it doesn't put a bus update because it is not sending the small values which it is changing, right? In SC and SM, on a write, we were just sending bus updates. So we were just sending the differences. Whereas here, I will do a flush. Flush meaning I'll put the full block onto the bus because the new reader wants the complete data. It doesn't want the small changes, but it wants the whole updated block. Okay. However, the state still remains SM because the new request is for a read. And the current cache is still the owner. Okay. The other option is we are in SM and there's a new cache wanting to write to the block. So processor write or a new writer comes into the system. Now, when a processor wants to write, what does it do? Let us backtrack. When we were here, we had the block in read. We wanted to write. What did we do? We simply said we got a processor write request and then we sent a bus update. So bus update is the signal which tells others that I have modified the data. Okay, now remember this. Coming back to state SM. Now SM, the current cache has modified the block. It is happily changing the data. Suddenly, there is another sharer who wants to modify. It modified the data and it sent the bus update to us. So what did we see? We did not see a bus read X. In messy, you see a bus read X. Here you see a bus update. So while in SM, look at the red arrow, you get a bus update. And when you get the bus update, what do you realize? I have to update my cache with the new item. And now there is a new sharer or new writer into the system. Hence, I cannot stay in SM. I have to move to SC. So from SM, on the red arrow, when I see a bus update, we update the local copy and move to SC. And what happens to the state SM? Now this state SM will be given to the new writer in the system. Okay. Similar transactions happen through M. And so overall, in Dragon, it is an update-based protocol. Multiple caches can share the block. At the same time, exactly one can change. So there is exactly one SM state, and there are multiple SC states. Is the memory updated or not updated? So generally it is not, because once a cache has SM, it is going to be the owner and it is going to provide the block using the flush transaction. However, when this cache wants to delete the data, that is cache eviction, this block will be written to the main memory. And of course, the SC already have the updated copy, so they need not be updated, but the responsibility of updating the main memory lies with the SM block. Okay, so I guess we've done one-to-one comparison and then seen the differences. So Dragon is update-based and Messi is invalidation-based. Invalidation, so there is only one M and multiple S states. Yes.
So, ma'am, basically in Dragon, let's suppose our cache block has, let's say, 16 bytes, and only 2 bytes have been changed. So those 2 bytes which are changed in Dragon protocol, only those 2 bytes are updated across the entire processors thing.
Ideally, yes. Ideally, yes. It's an optimization, but see, it depends on the implementation. So we cannot put a rule. Yes.
Okay, but generally this is like updates are basically small updates.
Small updates, but, yes.
And in the previous protocols that we have studied, like MSI, VI, and Messi, basically we invalidate the entire block and we update the block from the memory directly. We don't get these small updates basically.
No, because the block is deleted, and once you have to read or write again, you have to load the complete block from the main memory.
Okay. So bandwidth-wise, basically, Dragon protocol is much more efficient in terms of memory bandwidth compared to the previous ones. Like in
but it depends on the pattern. It depends on the access pattern. So if you in this, you can think for yourself that I have a system where there is a cache which is going to do multiple updates, several updates at a time, and when it is updating, the other shared applications will not access this data. In that case, Messi is good, because in this scenario, if I am using Dragon, what happens is I am doing a for loop of updating the variable X. And if I run this loop for 1000 iterations, every update I have to broadcast on the system. And whereas the other caches may or may not be interested in this data. So in this case, if there are consecutive several writes which are not interfered by other accesses from the other processors, then Messi is good. But if there is a scenario where there are two applications wanting to read write to the same variable, say 5 times here, then 5 times in the second one, and back and forth. So when there's a back and forth update across applications, then Dragon would be good in that scenario, because each copy will already have the data. Otherwise, you will keep on, if I'm using Messi in this scenario, I will unnecessarily keep invalidating. So the invalidation will become a ping pong effect. I invalidate your copy, then you write it, then when I want to write the way, and vice versa. So this is going to happen. Okay, so depends on the application.
The issue of false sharing that was there, like I had this thing, like is the same thing, like the false sharing is called, yes. So false sharing that happens.
Similar concept, we can say.
Yeah. Okay, ma'am. Thanks, ma'am. That's all from my side.
Thank you. Okay. So let us take questions from this. On the live session. Oh no, sorry, the sheet. So there is one comment which is a very long comment from a student, and so then there are two small questions. So we'll take those questions first. Okay, so the first question is, okay, let me take it from the bottom. How to grasp the multi-core data processing mechanisms for cache, shared bus, and memory in its entirety, including various protocols taught, as they seem quite overwhelming. Okay. So the question is that it covers the whole subject as such. So the question is that I have a multi-core system, multiple caches, shared cache, bus, coherence protocols, and how does this whole thing fit together? Um, yeah, so thank you for the curiosity. Definitely, it is overwhelming to begin with. But as a student, if you have done the basic computer organization course, so okay, so pedagogically, what we do is we teach you courses in small pieces and incrementally. So we start with a digital design course in an undergrad program where you learn how to design those circuits. Then we go for an organization course where you don't see many details. You only see a simple processor, a CISC-based or a RISC-based five-stage pipeline processor, a single cache, the main memory, and the memory organization. So that's a small processor system. And then when you go for advanced architecture courses, you will learn that these five-stage pipeline processor, which you studied in a basic course, it's very simple. If you use that, it is not going to be very beneficial and its performance is not going to be so high. Hence, I have to use this pipeline in a best way. And if I exploit parallelism, it is going to cause data hazards. So you have these hazard handling units to be studied. So when you study third level, say advanced architecture course, you have to understand how do I utilize the five-stage pipeline in a better way by handling the data hazards and the control hazards. How are these hazards handled? By designing small digital logic units which sit as part of the control path of your five-stage pipeline. So these are small controllers in your five-stage pipeline which will handle the data hazards and the control hazards. Okay, so this is a small increment in your understanding and your learning. The next stage is when we realize that this pipeline is good, my hazard handling unit is also implemented, but I still have scope of improvement and giving good performance, because when my application is doing a memory access, it is going to be stalled for longer time. So when it is stalled, can I do something else? So it's like keeping the processor busy continuously. So if you have to keep giving work to somebody, you have to keep thinking what work to give and how to enable that work. Hence, in a five-stage pipeline, once we have finished the best optimization which we could do for a single application, we become more greedy and say, can I run another application? Can I do look ahead because this current instruction is waiting for the memory? Can I run some newer instructions? But when I run those newer instructions, the answers of those should go to the memory in the program order. So how do you do this? You design a new logic unit called the reorder buffer and you do out of order execution. Okay, so this is a new development to the same design. So I do an out of order execution unit. I have to design the algorithm, design the hardware, that is the reorder buffer, the load store unit, and a lot of those things. Okay, so you do all of this. And when this is done, the complete system runs as an out of order single core system. So it's a single core processor. So what have we've gone through pedagogy of a simple processor, pipeline processor, hazard logic, then out of order. This itself is very overwhelming because, but if you see it slowly, step by step, you will understand that this is what I design. Once that design is finalized and stable, you design a next level and the next level. Okay, so with this, which probably you have already studied as an advanced architecture course, you have achieved a complex out of order processor. Next comes our target of having even better performance. And then as the initial 2 lectures of my course told you, the motivation of multi-core revolution, we will have multiple processors. And when you have multiple processors, I'm going to give different applications to them. Well, they will run nicely. But if I have a shared application which is running across different processors, then how will it run? Okay, so this is a new problem. So when you want to enhance the performance, when you have a performance or an energy objective, you have to come up with a solution. And that solution is going to entail design changes and correctness issues. So when I bring 2 cores, which you already designed as an out-of-order processor, when I connect these 2, I have fewer problems to handle as a computer architect. How do I connect them? How do I manage the memory? Each of them had a cache. Should I keep the caches separate, or should I join them together as a shared virtual cache, unified cache? Or can I have multiple levels of cache? Okay, so things build slowly. So don't get overwhelmed. Evolution and inventions, they didn't come all 10 together. They came slowly over several years, over decades they have come. So don't get overwhelmed. Try to understand every concept nicely, appreciate it, and don't forget that concept when you are adding a new layer. So every new layer, you have to be alert of what is sitting below it. Okay. So we discussed there's multi-core, and lots of data gets getting processed. We have caches, we have shared cache. The shared caches can be connected using a bus. You can have an interconnect and so on. Okay, so now when we put a shared cache and we allow multiple cores to read through this shared cache, there could be conflicts that multiple go to the same location to read, or if one independently writes, I'm going to get correctness issues. All right, so any evolution or invention in an architecture, because it's an engineering subject, you have to look at the improvement. You're looking out for performance. You are looking out for best utilization of your multi-core architecture. You want to keep the processor busy 100%. To keep it busy 100%, you have to give it some work to do. And this work has to be done correctly. It has to be functionally correct. Your software should give you the correct answer. It should not give random answers because it went to the memory which was busy doing something else. Okay. Hence, when a problem comes, you invent a new solution. You have to sit back and think about the performance, the design correctness, and whether it is giving the functional correctness also. So slowly, if you understand all these concepts and appreciate the stages of invention and the pedagogy or the order in which you were taught these courses in your curriculum. So we don't teach you parallel architecture in year 2. We teach this as a advanced level elective because you've already studied the below levels. Okay. So I hope it satisfies your curiosity. If you have further questions, we can take it up today, or you can put the question for the next live session. Okay, thank you. All right. Okay, so the second question is, in a large-scale parallel computer system with thousands of processing nodes, how does the choice between a shared memory architecture and distributed memory architecture affect the scalability of the system? Okay. Right. I would say that we have a similar concept covered in this subject when we do the distributed memory-based architectures, the SCI, Origin, and other protocols, maybe 2 weeks down the line. Okay, so however, to set the context, the question is, how does a choice affect the scalability of the system? All right. So I cannot have a 1000 node system, for example, with only shared memory. Can I have a 1000 node system with only a distributed memory? So that is the fundamental difference which we want to identify, which is best. Okay, so a shared memory is good when it is close proximity system. I have a common interconnect. The latency is reasonable, and we are able to also manage the cache coherence. it is a scalable or decent enough cache coherence protocol can be implemented in a small setup on a shared memory system. But when my system grows to 1000 nodes and I want to manage, for example, I want to manage a snooping based protocol, the messy snooping in a 1000 node system with a shared memory, what will happen? I need to broadcast my invalidation request. I'll just take one example. I want to broadcast the invalidation request and it has to reach all 1000 nodes. And it's going to take a long time. The nearby nodes are going to get the invalidation early, whereas the far off nodes are going to take longer latency. Okay, in such a system, I cannot rely on just sending the invalidation and starting the update. Because if I send an invalidation, I'm not sure that by the time the last processor, farthest processor receives my signal, whether I am permitted to modify the data item or not. Okay, so I'll be able to modify the data item only when the invalidations have happened. So there are these challenges when I use a particular setup for a larger system. If I'm using a distributed memory, then it manages its own small clusters. So in general, if I have a large system, it is advisable that I use smaller clusters of shared memory, and then across the system, I have a distributed memory system. So this is at the architecture level, what we provide. But these systems are best exploited at the software level or at the systems level when the system architect or the scheduler is going to schedule the applications locally. Because even in a distributed system, if my application wants to access data which is very far, again, the same problems of latency are going to come up. Maybe not correctness issues, but performance issues will come. Performance bottlenecks will come. Hence, your application and the data should lie locally or at least in the vicinity, the nodes which are closer to you. So these are application mapping type of a scenario. So this is how bigger systems get managed. Okay, so that's how a scalability is increased by managing the best of both across the whole system. Okay. Now I'll take the next question. So in this question, the student's background is more from instrumentation and control, and the student has done more circuit level courses, whereas our course turns out to be more theoretical. And the student wants to understand that once this course is completed, how can these things get implemented, or how is all this fitting into the real application world? Because everything is at the end of the day circuitry. Okay. So in general, the query is how is this mapping to a person with a circuit level understanding, and what is the future scope, or how do you get in-depth understanding of things happening on ground? So exactly how things are working in real life. Okay, so I'll try to answer this query. Okay, so from the circuit level perspective, see, again, referring to my previous answer during the current session about the pedagogical development or the way we get introduced to a variety of topics as we study them. The digital course taught you how to design multiplexers, adders, multipliers, the SRAM memory, and in organization course you studied the DRAM structure. So these are all circuit level things, although at the digital level, but You know, when I store a data into the DRAM, it goes as a bit pattern and it goes as signals on the data bus. Finally, then there is a bit line, there's a sense amplifier, and the data goes and gets written into the DRAM row. Okay, so the DRAM location gets loaded with a signal which comes on the data bus to the DRAM. So this is the circuit level understanding of a memory write. When you do a memory read, the DRAM is going to bring the data into the row buffer. From there, it is going to travel through the channel and go to the cache. And inside the cache, it is again written as a bit pattern. You know, the SRAM design, it is a 6-cell transistor design, which is used to store a single bit. So if you have 64 bytes of data, these many bits are there in the SRAM, which will be either 0 or a 1 to match your pattern. So that's the circuit level understanding of the memory. Then what is a circuit? How do I understand the cache coherence protocol from a circuit point of view? See, we also looked at the organization of the overall organization of a system where there is a Snoop controller, then there is the request table, which is accessing the bus and so on. And every cache is associated with a FSM, which is moving from state M to E to S to I, right? So all these state transitions. Yes, this is very theoretical, but this has to be implemented, and implementation is digital or eventually become circuit level. So how do I do this? So you will need to translate your method into a hardware description language, Verilog or VHDL or System C. So when you translate to that, from there you have to use either synthesis tools at your level of understanding. Otherwise, you can also consider that you want to translate it by hand or by some methods to the final controller design. So either you can design the controller by hand, or you can use synthesis tools to translate your algorithmic idea to a hardware design. So, okay, so this is how I translate a high-level flowchart to a netlist. So you write it into a Verilog, then you synthesize it, and then you get a netlist, which is a circuit level. Now, this circuit level design is going to fit near the cache controller to do all this coherence messages, read mechanisms and writes and so on. So all the data input, output, control, everything is going to be in this hardware, which who has designed? You can design it. You design an algorithm, write it in Verilog, synthesize, and then integrate it with the system. Again, it is not very straightforward because we are looking at a small unit in isolation. And as a student or as an early career researcher, you are not going to do the complete system. You're going to design small components. And once you become expert in that, then you can fit into the big picture then you will know how do I join components and so on. So it's similar to an object-oriented programming or a modular-based design where we design these small modules and then you have to combine them to make a bigger picture. So this is how, that's what I could understand from your query related to the circuits aspect. And if you want to understand how this works at the system level, then you can use the simulator tools, which are there open source, and which will simulate your multi-core environment, and you can run a program which runs on these multiple cores. You can also enable the type of a cache coherence protocol. You can say, I want to run MESI protocol on a 4-core system. I run this application, and you can put enough debugging statements in there to see how it is actually executing the coherence. How are the different states going from invalid to shared to modified and all that. So that is possible if you can try this out on a software simulator. So that will give you an understanding or a feel about how the coherence protocols actually coordinate in a multi-core setup at the software level, at the systems level. And as a hardware engineer or hardware designer, whatever the FSMs which we study in the class, you have to translate it to a Verilog code, synthesize it, and get the final design. Okay, so that's the circuit level thing. So I have tried to answer your curiosity. If you have further questions, you can ask now or in the next live session. But thank you very much for your interest, and I appreciate that with the circuits background, you're trying to understand this course. Parallel architecture course, yes, it is theoretical, but at the same time, it is equally digital or more systems course. So it's an interdisciplinary course between the two disciplines. And I appreciate that you are trying to understand and are able to follow it. Thank you. Okay. So there are no more questions in the Excel file. If there are some people who want to ask it online, we are available.
Ma'am, can you explain like what is the meaning of atomic bus? Like, what is difference between regular bus and atomic bus? Like what is this thing?
Okay. So we have this atomic bus and a split transaction bus. So
Yes.
atomic bus, it's an assumption that atomic word means when I do something, it finishes before I can do something else, the next operation. And so atomic bus concept guarantees that if a particular transaction is happening, it completes before the next one can begin. And you can, and the other design is the split transaction bus, where we can permit multiple transactions in parallel. Okay, so there is, suppose I want to do a write and we acquire a bus, send the write signal. First, we send a request signal to the main memory that I want to write. You can't simply send the data because if the memory is not ready to receive the data, it will get lost. So there is a protocol of the network or the bus network, which you have to follow. So you will you will send a request. Once you get the grant, you have to send the write, and then the data can be put once the memory sends an acknowledgement, for example, that it is ready to receive the data. So you will send the data onto the bus. And once the data is finished, the memory says, okay, I've finished the work and now we can do the next operation. So this is an atomic bus where until the write is finished, nothing else can happen. But one can argue again, because from the performance perspective, this is very slow. The memory is going to take time to write the data. And in the meanwhile, this bus is engaged by a single processor. So the other processors will face starvation. So what do I do? Can I permit this bus to be used by others? And for that, I will need to conceptually change the design of the bus. A semantic level I have to change from atomic to split transaction. When I go to there, then I have to handle multiple problems because I have to store the state of the system, who was doing what, and who finished at what time. So that segregation across processors has to be done. But then we do this for improved performance. That is the basic difference. Atomic bus is also going to do the small, tiny operations in the middle, but conceptually, it says that this is the only thing you can do, and I will not permit anything else to happen in the middle. Okay? Yeah.
So, ma'am, basically, these simpler systems like embedded systems and like FPGAs, like I have seen that they have something called atomic bus, like on their system. Like we have a small SRAM, like 50 something kilobyte, with basically atomic bus. It means that these bus they don't have that complex logic of scheduling and all that. So they just do one instruction at a time.
Yes, it can do one task at a time because it's a tiny system. To implement this, you already know that the protocol is so complex. You need these tables to be maintained. Again, some handshaking happens across them. Then the order in which the request finish, in order request completion, out of order request completion. Then there is a conflict across requests, two requests for the same block coming. So you need to handle several things when you permit multiple operations to take place. And once you want to do this, your controller is going to be heavy. The hardware which is going to do this control is an extra overhead for your system. to improve the performance. And for small systems, it cannot afford that much control logic. And the other reason is that these systems are not designed to handle such heavy parallel tasks. They are supposed to do focused objectives. And for focused objectives, an atomic bus is good enough. So it's not a compulsory thing. It is a design decision.
Thanks, ma'am. Thanks a lot. I understood this thing.
Great. Thank you so much.
Ma'am, but just one more query. Like, I was doing some a comparison between vector processors and array processors. It is in the first week, and I did some research on the topic. Like, this array processors have different uh, execution units, like a GPU, something like that. And this vector processors is something like Intel's AVX. It has a single processor, but it is very powerful. And it does have these parallel registers, and it uses pipeline-based parallelism. So I just wanted to ask between these vector processors and array processors, which one is more scalable design compared if we compare both of them? I think, ma'am, you are mute.
Yeah, sorry. So the architectures which we discussed in the course are the basic foundational designs. And if you're looking at the recent research articles or implementations, they are going to be different than the textbook designs, definitely. Because these, as we say, pedagogically, we teach you smaller designs and then we go to industry scale. But I would say these vector units have a different purpose of doing the same operation if I have many things to do at the same time, then it is better. But in an array, I can do different operations in parallel. So vector is like I want to do an array, a big array to be processed where I have to add all of them. So simply send it as a vector. But if I don't have an array of size 100 to process on, then most of my units will remain idle. And in that case, in a vector, I can't use them, but in an array processor, probably if I can schedule some other operation to that particular hardware, I can do it. So end of the day, every design is good as long as you are able to utilize it 100%. Okay, so you have to understand its design philosophy, what it is. For example, pipeline versus non-pipeline, then out of order versus single, a systolic, an array-based processor versus a vector processor. So understand the design philosophy, why it was designed for what kind of applications. And if your application is not of that kind, then that architecture is not good for you. The decision metric is performance. You have to improve the performance of every single application. At the same time, make sure that your hardware is utilized to the maximum. If it is remaining idle, then it is not the correct design for your usage. Okay, so with this in mind, you can evaluate across designs. So I do not know the architecture which you were looking at, but this could be a way to think and move forward.
Actually, ma'am, I was comparing from very basic designs like the Cray 1 vector processor, which was the earliest one. And along with, on the vector side, I took Neon from ARM, I took AVX from Intel, and the previous one, Cray, which I mentioned, like these were the three ones from the vector side. And for the array processor, I just took the NVIDIA GPU. So I took that thing on the other sides, and I was just comparing their architectures to find out like which one is better. And GPU is basically like from what I was trying to find out, it is not uh, an ideal array processor. It behaves like a vector processor in some ways as well, and also like a array processor in some other ways. So it was not like, because it does have some like on-chip vector accelerators as well. So
Correct. So see, these, that's why I said the definition of these processors from the pedagogy perspective are fixed. This is how it is. But the real implementations vary. As you yourself said, that the GPU can do much more than what our basic understanding is. Like it's an array processor, but it is able to do multiple things because of the implementation, or when you deploy it, you see that if I add these things, my processor is going to run faster. So the best way to compare is how have the processors scaled. But for example, you started from the Cray to the current vector processor. So you look at the evolution from the data handling perspective, the size of the data they can handle, the instruction size they can handle. So that is the evolution trace you can do. And for evaluation, you can look at what type of applications can run on one over the other. So I do not have answers for this, but as you're curious, I would advise that you explore the benchmark applications. I discussed the concept of benchmark in my subject, right? So you take different benchmark applications and see if you take a machine learning workload, which runs an inference engine, which works best on GPU, can it run well on a vector processor? Okay, and vice versa. So this will give
Yes,
you
ma'am.
an
Actually,
insight
I did the
about how
same
it
thing.
works.
I did what you mentioned. Like I used the NVIDIA's NV profiler, and I did the stuff that you taught in week 6, basically, which was the false sharings. And basically, if the CUDA program was done in a different way, due to false sharing, the difference was like, let's say 20x difference in memory bandwidth was registered.
Acha.
So
Great,
I tried it. So. And then thanks for the in your last slide session you shared about this Gem5 simulator. And
yes, I had mentioned that.
yes, so Gem5 simulator, and it was quite helpful in like understanding all the cache coherence topics, because it allows you to create your custom board. So I think it should be something written on the course itself. Like Gem5 simulator should be a part of this course now.
Okay, yeah. See, actually, it's already a 12-week course, a very heavy course. I could not even, the networks portion, the interconnect also has to be covered. But probably, thank you for a good suggestion. We could, so this is important as from the student community. If you can give feedback of the topics which you think can be replaced with other interesting topics, because we have to fit everything in a 12-week course, or we have to design a small shorter course which is subsequent course to this, where you can do some hands-on from the topics we study here. But it's a good suggestion. We'll keep it in mind for future. Thank you, and very nice that you're trying out.
Like yes, 4-week course on Gem5 will be like very good as a like companion course to this one.
Great. So I'll keep it in mind for future, definitely.
Thanks.
Let's see how things go. Thank you so much. And keep up the spirit and do something good. Okay, so if there are no more questions, we can close this live session. Thank you to my team to join. Thank you to the students who came live. Thank you to the students who post their questions. And I hope they will look at the live session video later on to clarify their submissions and doubts. And continue with your assignments. Watch the videos and keep that curiosity alive, because until you are curious, you will not understand what is being taught. Otherwise, it becomes a simple subject to read and to clear the course. So keep the curiosity alive, see the live session, see what other students are doing, see your performance in the course, and keep studying. We have 5 more weeks to go. And best of luck, everybody. Thank you, my team, and thank you to the NPTEL team of IIT Guwahati. We can end the live session right now. Thank you so much.
Thank you, ma'am.